All right, back to it. So the first thing, as I mentioned during the course lecture, is to create a sketch. So here's the quick sketch I've done and scanned in. The main features of this model, of course, are the seam height or the mining height, uh, the, the 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 pillar dimensions. So this view is x and z vertical, x across. This one is kind of upside down, y is pointing down and x across, but it doesn't matter. And you see I've allowed for rectangular pillar. So we have half pillar width, I've got a variable assigned there, half pillar width x and half pillar width y. And then the road widths are obviously going to be the same in both dimensions. So a few conventions or things that I like to do because it allows me to reuse bits of code is for the boundaries of the model. I'll basically call these consistent names xmin model, xmax model, and the same for y and z. And then I'll have kind of an arbitrary labeling process for um, I'll have dimensions input, and then from the dimensions I will set these coordinates, if you like. So I've set YP as the edge of the pillar, XP as the edge of the next pillar. And because it's such a simple model, I don't need a lot of them. I'm just going to set the center line of the pillar at Z0, um, and then I'm going to have ZR for the roof and ZF for the floor. In terms of mesh, what I'm going to do is going to try and have the I'm going to grade the mesh density from this corner, which is also this corner. Um, try and have it the same across this region, and then grade it away from there. Okay, so we can just get stuck right in. We know what we're doing. We know what the geometry looks like. We need to, of course, ask ourselves why we are doing this model and what we're going to get out of it. So, of course, we're doing this model so that we can look at how what the strength of the pillar is as a function of its size. Now, there's two fundamental ways of going about that. We can either simulate the mining at the depth that it's going to happen with different pillar dimensions, or we can actually load up the pillar um, and set up different sized pillars, load them up to failure, and then create our own little pillar formula, if you like. Okay, so let's get stuck into the data file part of things. So this is where I create my data files. It's a program called Text Notepad++. It's got some very nice features, and I've kind of programmed it over the years to recognize all the fish commands. You can put any of the typical languages, programming languages in there. Um, and this is the new fish language from version 6 onwards. There's a version 1 for version 5 and before as well. So I'm going to go through everything in a fair amount of detail here so you know what's going on. Um, the first thing to do, of course, is always to say model new. That clears all the old data. If you don't do that and you call a file, when you've got an old project already run in the background, it'll try to superimpose all the data and you'll end up with a big mess. So first thing, model new. Model large strain true, and the comment there I've put is always use large strain, which is very true. You always want to use large strain if you can. Um, another thing I mentioned earlier, model history mechanical ratio. So you always track the history of the mechanical of the maximum of the unbalanced force ratio, so you can see whether the model is approaching a steady state. Now from here, you'll see there's a call. This is a hangover from a previous um, data file that's calling a subroutine in a different file. We don't actually need that, so I'm just going to take that out. So the first thing I do, fish define control data, and then call that. You might ask, why don't I just put that over here somewhere next to these models? But remember, then it will be interpreted as a FLAC command and not a fish instruction. So the fish instruction I want to do is say the file root. So all my outputs from this model run are going to be are going to be prefixed with this phrase PILLEG, and that's stored as a string. Now, in terms of procedure, the interpreter is going to go execute these three. As soon as this file is called, it's going to execute these three instructions. It's going to log that it knows what control data means, and then it's going to run control data. And all it's going to do is set that variable. Now, what I also like to do is set a number of flags. So flags are basically booleans. They're trues or false, or they can be numbers as well. That control the program execution. So debug un is something we don't actually need for this particular model. Flag elastic is just for an initial run. You might want to not run all the strain softening properties in, which is quite reasonable. So I'm going to say flag elastic false. Flag solve. Now this allows me to, if I've got a run with a lot of stages to it, I can just test that the stages actually work, and I don't then need to go and excuse me, I don't need to wait for each stage to solve before I get a result. That's set by default here. Flag plot is whether or not I want to output the plot files, which can also take a while. Flag save, whether or not I actually create save files regularly. These are very large files, so often you don't want, if you're testing phase, you don't want to output the save files. Flag preloads is not necessary. Test steps, sometimes you want to run one or two steps just to initialize data. In the case where we don't solve, we still need to run a couple of steps just for all the stuff to get initialized. That's particularly relevant for the interfaces. Mechanical ratio, the default is 10 to the minus 5. We'll keep it there. And then I have a small value for proper comparisons. You should never say, if x is less than, if x minus, or if you want to compare floating point numbers, so real numbers, you should always subtract it from your target number and then see if the difference falls within a range, rather than comparing it with comparing floats with floats will nearly always give you problems later on. So the next, you're going to see I'm going to shamelessly borrow from other files here, which is no problem. So a couple of these I'm actually going to use again. So I'm just going to pop those in there. So fish defines setup variables. This is where I set up the variables that define the model. Okay, depth to floor is one of the variables I might use later. We'll see. Okay, the way I like to set it up is so that you can go to this right at the start of the file to this routine, and you can change everything you need to. That's going to apply across the whole of the model. So as I mentioned there, we've got this varies between from 4 to 5. Let me check actually. So it's, let's say 2 and 4. Let's just make it 2 and 4. My initial pillar width, let's say for argument's sake the seam is at 100 meters, or let's make it interesting. Let's make it 200 meters depth, which is, let's do something crazy and go even deeper. Let's go to 400 meters, which is very unusual in South African coal. So I'm going to have a reasonably large pillar. My road width, I said there I'm going to have 7.2. Mining height or seam width as I had it there, let's keep it at 4 meters. There's no coal on the roof, so I don't need any of those right now. And then I'm going to go back to my sketch and see, okay, what values am I going to use later on? What do I need to derive from these input values? And what else do I have to set? So the roof height and the floor height is something I haven't set yet. Let's see. So roof height is, I'm just going to say 20 meters, why not? And floor height is the same. Those two should probably be the same in most cases. Let me check what else I'm missing here. This is determined by road width and half pillar width. So I don't really need to set anything else for now. So I'm going to put the derived values here. So those derived values include Z floor and Z roof. So let me just set that up. Z floor is, if I've set Z, I've set Z naught at the center over here. then it's going to be minus mining height over 2. And my Z roof is going to be the positive version of that. Okay, let me actually say that Z naught equals 0 as well. And you notice I'm quite religiously adding my decimal points there so that it knows it's dealing with floats. I need to specify xp and x1, so and yp. xp equals simply pillar width in x over 2. And you'll see there's a lot of copy pasting going on here because I'm changing only a few little things. Okay, I think that's all I need. Oh, and all the Z maxes and Z mins, etc. Let me set that so long. X min model. It's on a symmetry plane, so I'm going to specify it as 0. X max model will be obviously xp plus road width. And it's going to be the road width over 2 because there's a symmetry at the center of the road width as well. And again, I'm going to copy that straight into Y. Very useful feature. If you press Shift and Alt, you can select rectangular areas in text in Notepad++. I can just change that like that. YP plus road width remains the same. Alright, Z min model. This is going to be slightly different now. Equals, it's going to be Z floor. This is a negative coordinate. Now subtract the extra roof, the floor height from that. And I'll have a similar thing here for the max. So Z roof plus roof height. Is that right? A very useful feature as well is you can just double click on that and you can see it's highlighted again up here. So I know that it's been set earlier. ZR has been set. Those values have all been set. These unique variables, I didn't bugger up the copy pasting operation. Yeah, so I know that it's all going to work nicely. Okay, alright, and of course to get this thing to actually run early on, I need to put the @ symbol and that thing. Okay, and of course I need to save the file. What did I call it? Pil.eg.dat. Okay, there we go. Alright, and I'm just going to stop again.